Imagine the most cutting-edge robot you might have ever seen, straight out of your favorite sci-fi movie or from the self-driving car revolution that you were promised would have already reached you. Now imagine a farm, better yet a small farm, somewhere within the African continent. One would be forgiven if they thought that, in this context, one didn't have much to offer the other. It wouldn't even surprise me if you thought that one could, if not properly regulated, damage the other by disrupting the labor market. My name is Paul Amayo, a researcher in the Department of Electrical Engineering at the University of Cape Town. And in this talk, I instead offer a more collaborative approach, whereby the key insights as to how contemporary robots understand the environment and the space around them are merged with the deep domain knowledge that farmers possess and readily utilize to boost African agricultural productivity. So what can robots offer our everyday farmer? It turns out that for robots to operate safely and successfully in any type of environment, they need to have a really good understanding of it. This understanding ranges from knowing where obstacles are in some of the simple robots to interpreting road signs and traffic lights in self-driving vehicles. Roboticists, as we call ourselves, have therefore taken great pains to ensure that any robot that is put into the world has a high-resolution, three-dimensional internal model of what the world is. As safety is a huge concern from robotics, this internal model must be very accurate, down to the nearest centimeter or millimeter. This is a little bit different from how humans perceive the world. If you could indulge me for a bit, and using your hands, try and imagine what a 1 meter distance looks like, and then ask somebody else to do the same. I can almost always guarantee different results. This is because humans, such as me, are not always overly concerned with geometric accuracy and are often not great at it. Rather, it's the relationships between objects in the environment that we pay attention to. For instance, it is quite intuitive to know when to stop running when approaching an obstacle. The precise distances and speeds are not calculated, but your brain and body know when to stop. This brings us back to our farmers, who can understand the complex relationships between seasons, weather conditions, and crops without having to rely on quantitative data. There is a limit to this, however. As farms get bigger and as new techniques hit the market, it becomes more difficult to keep track of these relationships, and quantitative data becomes more and more useful. Current access to this data and the associated insights is, however, limited to those who can afford both the sophisticated equipment, such as drones, and the expertise required to operate them safely and process the data outputs. The research work, led by my lab in the African Robotics Unit, seeks to significantly reduce the barrier to obtaining these insights. We do this by understanding that when a robot obtains an internal and accurate model of an agricultural region, this same internal model can be interpreted by humans to provide 3D quantitative data regarding the environment. My lab primarily focuses on what are known as lightweight techniques for this robotics problem, using the most advanced techniques in computer vision and machine learning, but retaining the possibility to deploy these on cheaper and low-cost devices such as mobile phones. For instance, one of the biggest breakthroughs in machine learning in the last 10 or so years was the ability to obtain 3D geometry from a single 2D image taken by a camera. This has been behind the development of features such as face unlocking on most modern smartphones. As one can imagine, especially in our current society, security is a very important aspect. So these features need to retain a high level of detail and redundancies. It should be easy to see that this fine level of detail cannot automatically scale well from a single face to the much larger agricultural regions we are interested in. The lightweight techniques we develop must therefore intelligently drive down the redundancy while simultaneously retaining the accuracy. To do so, we make extensive use of mesh representations, such as those you'd see in video games or computer graphics. These representations easily fuse in redundancies and can therefore allow for the stream of images from a robot to be turned to a precise metric 3D mesh model. As this metric model can be further enhanced with precise crop location, tree yield, fruit sizes, plant health, to name but a few, it provides a rich source of information on the agricultural region from the robot's internal model that can be presented to the farmers. So in this talk, I presented an approach to harnessing the technological gains that have been made through robotics in a symbiotic manner with the agriculture community. It isn't quite the cyborgs of your sci-fi nightmares, but by combining the farmer's experience and intuitive knowledge with these robot-equipped mobile phones, we can obtain deep and meaningful insights into the agricultural sector, boosting its productivity. Given the looming threat of climate change and the realities of a growing population, it is critical that agricultural productivity is bolstered.